Friday of midterm week. We're halfway done. Not exciting? Woo-hoo. So we've got 8 more weeks, 7 more weeks of class, and a week of final. It's kind of crazy how fast it goes sometimes, right? So you've made it halfway. Congratulations. Housekeeping, I moved some dates on homework assignments because people asked. So I just moved them the chapter 3 and chapter 4 back, which I plan on moving to chapter 4 anyway. You have more time on chapter 3. Then I was asked by another student to actually work a couple of the sampling problems. And so here we go. So anyway, given in the question was, there's a compound XBr3, and the question is asking for the unknown metal to identify that. So X equals an unknown metal, right? And it gives you a little bit of information with it when it pops up there, maybe. Okay. Did I not get it on? Someday. Well, and the question, I think it changed. I mean, there's a random number generator for each of the questions. You guys realize that? And so it's going to be different than what I'm going to use because I worked out the problem over lunch today. And so anyway, but it gave me that there was 4.729 times 10 to the minus 2 moles of Br, okay? And in that relationship, then I also know the number of moles of the compound, okay? Because if I know the number of moles of Br, then I can get to moles of compound just by multiplying that times 1 mole of XBr3 to 3 moles of Br, right? You guys with me? And so now I've got moles of Br, and when I calculated that, I got 0.0158 mole of XBr3. Okay, so now if I have the moles, and then it also gave me the grams of XBr in the question, and the grams it gave me was 4.704 grams of XBr, right? You guys with me? So if it gave me the grams of XBr, and I know the number of moles of XBr, then what can I calculate from grams and moles? Well, like your way to the compound, right? So that's going where I want to go. So if I take that number, 4.704 grams of X, oops, I should have put a 3 up there. I apologize, I dropped that. That was unintentional. And then I divide that by the moles, and 0.156 times 10 to the minus 2 mole of XBr3. And if I did my math right, that means it's 298.4 grams per mole for XBr3. All right. Now, pretty straightforward to get to right here. But you're saying, where am I going? I'm actually doing this because I want to use the percent composition to find that metal's identity. Okay, so to get the percent of that relationship, right, is done with this number, right, and or I say that, actually I did that a different way. That's not true. You can do it that way. I went a different route when I was doing this, and then I looked at the way they solved it, and they solved it a little bit differently. But I gotta change markers, that one's dying. Watch what I do when they die. Don't want to get it again, do we? Alright. So the mass percent of VR is equal to the mass of the element divided by the mass of the compound. Times 100%. Would you guys agree with that statement? So the piece divided by the whole. And so if I could get the mass percent of VR, then 100% minus this mass percent will equal the mass percent of the unknown metal. Okay? So this is going to be equal then to 4.729 times 10 to the minus 2 moles of VR times the atomic weight of VR, which is 79.904 grams per mole. And so now I've got grams of VR and divided by the grams of compound, which was given right here, 4.704 grams XBR3. And so this gives me that times 100, gives me the fraction or the percent of HBr, and it's 80.33, something on that line, 80.32 is what I got. All right, so 80.32%. So what's my percent of that's X? What's my percent that's X? 80% is the VR. It would be 100 minus 80.3. So 19 or 80.232, excuse me. And so 100% minus 80.32% equals 19.68%. And once I've got that, then to calculate the molecular weight of the unknown metal, I take that value, 19.68, percent equals 1 mole of X times the molecular weight of X in grams per mole, and divide that by 1 mole XBR3 times the molecular weight of XBR3. And so this is the same expression that we used here, right, to find the percent of VR, but we're using it in the backwards direction, and we're going to plug in the pieces we know and then solve that. And so we have the moles of X and XBR, which is equal to, well, actually, while we're doing this, 1 mole times 298.405 on the bottom, and grams per mole. And so that gives me the grams per mole, and then 1 mole on top times the molecular weight of X. That's the value that we're solving for, and that's all equal to 19. We solve for X, and that's my molecular weight. Okay, so that's how you would finish that. For my numbers, that value was 58.69 grams per mole. And then I go to the periodic table and find the metal. What metal is 58.69? Cobalt? Nickel. 58. Well, cobalt's pretty close, isn't it? Right? So, man, that might be tough, but on my example, it was nickel. Okay? On my example, it was nickel. All right, so this is, yeah, go ahead.
Where did you get those 0.156 times 10 to the negative
5, 6, I may have changed that. That's the moles of XBR right here. That I changed that value. Or maybe when my calculator ran it was, I don't know. Yeah. Or when I wrote that, I flipped that, changed that number. I do that occasionally. Have you ever noticed that? Yeah. It does. So with that number, that's 4704 grams divided by the moles, and so that was an error. Good problem? Yeah, it's a good problem. That's a challenge, all right? It took me probably 10 minutes to work from start to finish on that one. It took me a second to get warmed up, okay? I have to admit to that. This one was easier, the next one. So this is the third to last problem in the problem set. I don't know the number, we can go back and look. Hang on. So that was 41, okay? And so then 42 is this one, and I love this one, right? A student, Ken. You guys have any idea what my first name is? Ken, yeah, Kenna, right? So anyway, good question. It made me smile when I read that. How's that? My granddad was actually Kenneth E. Garrison also, and so I got Kenny and Kenna, and they called him Ken, right? So I don't often go by Ken, except in grad school, one of my lab mates refused to use anything but Ken, and so that kind of stuck. It's okay, I like him. He's probably my best friend in the world still today. So anyway, this one says that there's 2 carbonate compounds, and this marker's dying. Wow. We have a stash, hopefully still here. Which color would you like? Blue or black? Two carbonates. One of them is MgCO3, and the other one is ammonium, NH4. There are 2 of those. And CO3, so carbonate is CO3 minus, right? You guys are probably familiar with that already. And it says that there's a mixture of these, okay? And so the mixture is 66% carbonate, 66.04% CO3 minus, okay? And then the question asks, what is the mass percent for the component MgCO3? Okay, so in that, the way I went about this was I decided to look at 2 equations because there's 2 unknowns, right? You guys with me? So there's an amount X and an amount Y of each of these that we're trying to find. Okay, you guys with me on that? And so I started looking at fractional relationships. And so what I did was I calculated the fraction, from the molecular weight, the carbonate piece, right? And then the total atomic weight, and then use that ratio to define a fraction, okay? The fraction of carbonate in each, all right? And it's to get to an equation which we can solve, which is the percent CO3 in X plus the percent CO3 in Y equals 0.62 or 0.6604 from this value for the compounds. And so anyway, so X being the amount of MgCO3 and Y being the amount of NH4. So I wanted fractions so I could have this equation to fractionally find those. Now, if I have two unknowns, what does that mean? Can I algebraically solve with just one equation? No, I've got to find another true statement, and well, in this, if I'm talking about X plus Y, they're going to equal 1. That's going to be my second equation. Okay, so that's an easy one in terms of those pieces. All right. So anyway, to get the fraction or percent CO or the fraction CO, then what I'm going to do is take the molecular weight of the CO3, which is 60.01 divided by 84.32. I got that magnesium is 24.31. This is 60.01. So 1 carbon and 3 oxygens. 3 times 16 is 3248 plus 24. Excuse me, not 24. Do what? Yeah, plus 24, that's right. It is. So that's the right number, I got it right. So anyway, so that fraction is equal to 0.7117, and the other fraction is 60.01 divided by 96.09, and that's for the NH4. There's 2 of those, CO3, and so that's 60 for this part. 14 plus 4 is 18 times 2, okay? And so that's 96 when you add all of those together. So that's the molecular weight for this compound. So I've got another fraction, and mass fraction is 0.6604. And so then I'm going to go down here and plug those fractions in, and 0.7117 X plus 0.6604Y equals 0.66. Is that right? 0.6604? No. That was my mistake. I pulled it on the wrong part of the page. 6245. All right. They both started with a 6. I just grabbed the wrong number when I looked down. All right. So then we rearrange this equation, and I solved it by substituting y. So 1 minus x equals y, and so then I plug that into this expression. 0.7117 x plus 0.625, 1 minus x equals 0.6604. I solved for x, and x equals 0.412. And so what we're talking about is the portion that's MgCO3 equals x equals that. If I convert that to a percent, then 41.2% MgCO3. So I used fractional composition to find that solution. Cool? Does that help? See it? This next one's a lot like that. Should I let you guys try that? And if you have struggles with it, let me know and we can solve it on Monday. Is that reasonable? Yeah. Because it uses the same types of strategies to get there as we did in the last question. We're using ratios again. And so in that next one, it's actually looking at pieces. It's saying that I have, I'll try to get you started on it, please. Good? Can I erase? Yeah? The next one says that I have a reaction where 204 grams of Cl2 plus 44.6 grams of phosphorus yield two products, PCl3 plus PCl5. So this is a total of 248.8 grams in the question I was given, right? So it's asking what is the fraction of PCl5, right? And what is the fraction of PCl5? And so in the same way, you guys are going to build some equations, right? X is for the PCl3, x grams, plus y grams PCl5 equals 248.8 grams, right? And then the other equation that I wrote was from the fractions. So I calculated the fraction, the percent phosphorus for both compounds, okay? I calculated the percent phosphorus for each PCl3 and PCl5. And so then I made a second equation, which was 0.226, which is the fraction times x grams of phosphorus plus 0.149 y grams of phosphorus. And that's equal to 44.6 grams of phosphorus total. So what I did was I took the fraction of phosphorus from each compound, right? Multiplied that times the total mass of each of the compounds, and to get to the weight of the phosphorus. Okay? So then, once I did that, I actually, since I made y, I made this one x and this one y when I set it up, right? Then I rearranged this equation in terms of an x substitution to keep y, because that's the fraction I wanted, and then I substituted into this equation and solved. Okay? So I'm going to stop there and let you guys see if you can't do that one on your own. Cool? Fun stuff, right? Fun stuff. Any comments or questions? Oops. Right here on shapes of orbitals, and we were talking about the periodic table. And when I look up here at the periodic table, then, and I ask you in terms of blocks, what you would call this block related to orbitals, what would you tell me? That's the S block. And if I asked you about this block, what would you call it? The P block. And then if I asked you about this block, what would it be? D. And then if I go down here, what's that going to be? F. All right. Is it possible to have, theoretically possible to have a G block? Yes. We just don't have any known examples of it, so we're going to ignore it. Is that okay? All right. So, now, those are the parts of the periodic table. We're going to use those heavily. All right. Now, orbitals have shapes. I think the best way to do that is to actually look, right? And so what is an s orbital shape? Looking at it. It's a sphere, okay? So instead of being a circular orbital like Bohr proposed, right, rotating like a planet, then we have a region of space where that electron would be found. And 1s is the smallest orbital, right? Most contained. And then we would move into the 1p orbitals, okay? And so, or the 2p, sorry, 1s, then 2s, then 2p. And so if we move into that, we get to those p orbital regions, and we have px, py, and pz. And so that's showing those three different orientations, and that's on an x, y, z coordinate system, and so you guys are familiar with that. And so we use x, y plots all the time. Z would be that plot coming out of the board on a planar situation, or as it shows it here in that XYZ plane. All right. So anyway, the D subshells. Okay. So I should ask the shape of the p orbitals. What would you guys call those?
Figure eight.
What's that?
Figure eight.
Figure eight. Dumbbell is the word that they use. That works, doesn't it? So that's a dumbbell shape. And so we can see that there's three dumbbells of equal size and shape. And so those are fairly easy to imagine. But when I move to D, then 4D orbitals are 4-lobed, roughly clover-leaf in appearance. And the fifth is a 2-lobed region that lies along the Z-axis with a torus or ring horizontally around its center. The shapes of the 7F orbitals are more complicated, having either 4, 6, or 8 distinct regions in which the electron is likely to be found. And so here's looking at our D picture. And so this is showing those clover leaves, 4-leaf clovers. It's pretty lucky, right? And so this is DXY, right? And this is oriented up in DXZ. And this is DYZ, so along that y-axis. This one is along the x. And dx squared minus yx squared. And so that's laying there in that cloverleaf pattern. And then the last one is the dz squared, and it's got the donut with the dumbbell. Okay? The donut with the dumbbell. So 4 clovers and a donut with a dumbbell. Sounds like a song, doesn't it? We should write that. Like avocados, avocados. Never mind. I think crimson and clover maybe is the place to start with that. Never mind. All right. Relative sizes and energies of orbitals, all right? So, since all orbitals of an atom exist around the nucleus at the same time, in the same space, right? So there's regions of higher probability, lower probability we find an electron. And the size of a particular orbital increase as we go down in principal energy levels, 1, 2, 3, 4, and so on, right? So as we increase that, and 1s orbital is a region of space that is entirely inside the 2s orbital, right? And the 2s orbital is entirely in the 3s orbital. So small ball, bigger ball, right? You guys with me? As I move up in energy levels, right? And then within a shell, the general order of subshells, the general order of lowest energy is S is lower in energy than P, which is lower energy than D, which is lower energy than F, generally, okay? So we're gonna throw that out there. That's important when we start doing electron fill, because when we fill, we put the electrons in the lowest energy level possible, okay? All right, now when we start doing bonding, then interesting things can happen, okay? And then combinations of electrons in the appropriate number can change the way that they fill. But you don't have to worry about that. In this class, we'll do that in advanced inorganic chemistry when you take that course. Okay, so anyway, relative size of orbitals relative to each other. Our atomic orbitals much smaller than this. This is a cartoon, right? And an atom is extraordinarily small, and so those orbitals are smaller than the atom, and the electrons exist to the size of the atom. And so with the 1s is smaller than the 2s, which is smaller than the 3s, as we were saying. And then the 2px, 2py, and 2pz are all smaller than the third energy level of those, okay? And so we see them increasing in size as we move out, which means that as I move down the periodic table, what's happening to the size of atoms? They increase in size, and as I move over, then what do they generally do? They get larger too, okay? So as I add electrons to the same energy level. Now, not always true, because of nuclear pull and arrangements can affect that, all right? So anyway, based on subshells that make up each one, how many electrons can each of the first three principal energy levels hold? So if I have n equals 1, right, how many electrons can I hold in that? N equals 1. How many orbitals are found in n equals 1? 1s, right? So how many electrons? Now what that's saying, how many electrons can each of the first 2 electrons? That's correct, all right? So if I move to n equals 2, okay, what do I have? I've got 8 total electrons, okay? And how many pairs would that be? 4 pairs. And so there's 4 different orbitals that we're talking about, or, well, an s orbital and 3 p orbitals, right? You guys with me? X, Y, and Z. All right, and then if I move to n equals 3, what happens? It includes 3s, 3p, and actually the 3d subshell. 18 total electrons, yeah. So anyway, so if we move down, then that's what we find. N equals 1, which consists of only one 1s subshell. And so 0 can contain 0, 1, or 2 electrons. If I move to the next one, then 1s and 3p orbitals, and I can go from 0 to 8 electrons. And then 1s, 3p, 5ds, I can go from 0 to 18 electrons. Cool? Yeah, so energy level diagrams. So we're going to learn to sketch those, and so we have to know what it is. They're just graphical representations. We try to draw them with the relative increase or change in energy shown, and each orbital is represented by a short line, and arrows are used for the electrons, okay? okay? Now, when I have electrons paired, then they have to have opposite spins, and so we have a custom of turning one of those arrows up and the second one down. Okay, you guys with me? One of those has to be plus 1/2 and the other has to be minus 1/2 in terms of spin. And so we acknowledge that in that relationship, okay? And so anyway, this is showing the arrangement. Here's our 1s, the lowest in energy, then 2s is next. So we would fill 1s, then 2s, then we would fill 2p, and then we would fill 3s, 3p, and 3d, and then we would fill 4s, 4p, and those are getting pretty close to the same, aren't they? But I think the next one is 4d, and then we would work our way up that. Okay, now it's not to say that we couldn't end up with a different configuration based on that, but those are the ones that we're going to start practicing with. And so here's an example. So if we pick the element neon, right? So we've got neon, and I like to use the periodic table when I'm doing this, okay? And when I go to neon, I have the 1s is full, the 2s is full, and then these 6 electrons are present, and so I end up right here. And so that means I should have a total of 8 electrons in that second shell. And so I have the first one with 2 always, and then 2, 4, 6, 8. And so this is showing that is full, okay? And in fact, that's a very stable configuration. And all of the elements in this family have that configuration in their left shell. And we call that an octet, don't we? In that relationship. And so we have a full octet because we combine that s and p orbital together. All right, so anyway, the off-bow principle or building up principle is a process of filling subshells from the lowest energy upward. Hund's rule states that within a given shell, if we have a single electron, it will be unpaired. Or even up to, like in a p orbital, if I have 3 electrons to put into p, they will go into one into x, one into y, one into z. I will keep them unpaired as long as possible. And then when I get to the 4th electron in that p orbital, I would put that as the pair. Okay, and then fill and so on. So anyway, if there are 2 or more unpaired electrons in a given subshell, they may occupy different orbitals, but must have the same electronic spin. And so here I go. If I'm looking at carbon, then 1s is full, 2s is full, and then I put 1, 2 electrons in 2 separate p's, 1, 2. Okay, and so full, that looks higher energy. And notice the spins of the 2 electrons are in the same direction. Here, notice they're in opposite directions when they're paired. Okay, if I move to nitrogen from carbon 1 over, then I fill that 3rd orbital that's empty. When I move 1 more to oxygen, then I start pairing, and notice what happens to the pair. The spin what? Is opposite again, okay? Always show those as opposite when you're filling, okay? When I have a pair. All right, you guys do one. You do the fluorine atom. So somewhere on a piece of paper, right? Do a fluorine electron fill. So what are we going to need to do that? What's the lowest line going to be? 1s. So fluorine, and I'm going to put a line 1s. And then 2s, and then 2p, and all right. And then you guys do the oxygen atom and the boron atom and see how you guys do, okay? Oxygen and boron. Oxygen and boron. So here's oxygen again. We'd already looked at that, but good practice to draw them yourselves. We see the 1s, the 2s, and the 2p. And second level having 2, 4, 5, 6 electrons, which is that position that it's in on the periodic table. Can you also use the total number of electrons for an atom to help you? Yeah, so electron fill. And so I would argue that how many total electrons should oxygen have? 8. And so 2, 4, 6, 8 is on the board, right? So there, we have the right number, so that's a check. And then we're going to do ions at times, right? And so when I make an oxygen ion, we're getting there, I'm jumping ahead. But if I have oxygen minus 2, how many more electrons does it have? It has 2 more, and so it's an ion, so it's holding those. So in terms of that, what does it have the same electron field diagram is? Which element? Neon, right? Which is a stable configuration where an element is happy. And so things want to be noble when they start making ions, and so oxygen becomes like neon when it accepts 2 electrons. Kind of helps to explain that minus 2 when that forms, or if I took lithium, for example, right? So everybody find lithium right now. If I make lithium plus 1, what's its valence shell like? Which noble gas? Helium, right? And so it's noble like when it gives up, and that's why it's happy. In fact, all the elements in that first family give up 1 electron to become like their complement noble gas in their valence shell. Cool? Yeah. So just trying to make a connection there so you guys see that and those relationships. Here's boron. So 1s has got 2, 2s has 2, and then 1 in a p lobe. All right. 1 in a p lobe. All right. Orbital filling diagrams. And so starting with the 3rd and 4th shell, the energy levels of the subshells begin to overlap. And so if, for example, the energy of the 3D subshell is in between that of the 4s and 4p subshells. And so an orbital filling diagram is used to get those in the correct order. And this is it. And you guys, every one of you can draw this in here. And let me show you how to do that. Okay? And so this is your fill order that you're going to use when we're doing energy diagrams and stating what the orbital fill is. But n equals 1, 2, 3, 4, 5, 6. They went down to 7. And 2s, excuse me, 2s, 2p, and then 3s, 3p, and 3d, and then 4s, 4p, 4d, and 4f, and are you guys getting the pattern yet? 5s, 5p, 5d, and 5f, and so on. You guys with me? And then you have to be able to draw diagonal lines. Okay? So I'm going to start filling here, right? And they used an arrow, and then I'm going to go right back to here, right? Fill 2s, and then 2p 3s, and then 3p 4s, and then 3d 4p 5s, and so on, right? And so I diagonally draw lines. I think you guys should be able to do this, right? On a test, when I ask you to start filling orbitals in the appropriate order, then you would write this out on the side of your test, and then to get those to fill appropriately. Okay? So, I will give it to you on the quiz, but I won't give it to you on the test. Okay? Cool? Alright. So
that's basically just explaining what.
that's where I'm putting electrons in, right? And so when I'm doing this, for example, to know which orbital to put next, then I use that, okay? Or I can use it to do electron configurations in the same fashion, okay? And so this is the electron configuration for neon, right? Where the 1s2 or the 1s is full with 2 electrons, the 2s is full with 2 electrons, and the 2p is full with 6 electrons. Okay? Do this for oxygen right now on your paper. Do the electron configuration for oxygen right now. How is it different from neon? So it's 1s2, 2s2, 2p4, right? 2p4. So that's an energy level diagram that's filled. So the energy level diagram is just, in my mind, another way of showing electron configuration. Okay? Or electron configuration is another way of showing electron or energy level diagrams and so on, right? So once you kind of get those connections, then that's what that's for. It just shows the arrangement, lists the subshells with increasing energy, adds a subscript to each, the superscript to each subshell to show the number of electrons, and the sum of the subscripts equals the total number of electrons in the atom or the ion. And so we're going to do the same thing we were doing here, but with electron configurations. All right, oh, wait a minute, we just did the one for oxygen, so here it is, just to check. Oops, next one. So 1s2, 2s2, and 2p4. All right, and then elements in each group of the periodic table all have the same outermost electron. Elements in each group of the periodic table have the same outermost electron configuration. What we were talking about a minute ago, all of these have the same outer electron configuration, all of these do. Well, I say that weirdly, right? We call it the octet rule, right? Talking about the sp combined and looking at these outer shells on these noble gases. But in reality, helium is different, isn't it? It should be like a duet octet rule, right? Because with 2 electrons, I'm stable when I'm really small. Okay, so anyway, this is just showing what I've been trying to teach you guys from the very start, the S block, the P block, the D block, and the F block. And so those are the subshells of the periodic table. So you're way ahead of this line, right? It's a good place to quit. It's colorful. It's a weekend, and I'm out of time. So